Today, we'll briefly discuss symmetric cryptography, block ciphers, and their most used modes of operation. We'll also have a brief overview of stream ciphers. The word symmetric comes from the fact that the same key for encrypting messages is also used for decryption, as described in the following diagram. Now, in here, Alice uses the same key for encrypting the message M via the function E for encryption, and send C, the same key that is used for decryption by Bob. Bob retrieves the message C via this communication channel and decrypts it using the same key that is used for encryption to get the message M. Since the same key that is used for both encryption and decryption, we call this symmetric cryptography. Symmetric cryptography has two categories: stream cipher and block cipher. Block cipher has a general method called iterative encryption. It is an encryption scheme in which data is split into equally sized blocks for encryption or decryption. Encrypting block starts by using a randomly generated number, and that is the shared secret between the sender and the recipient. Now let's have a look at what iterative encryption looks like. We first start by a random key generator. To get a randomly generated key, of course, as the name suggests, let's call it K. Then we get multiple subkeys from K via a subkey derivation algorithm. So we get K1, then K2, and so on until we reach the final subkey KR. We get some message M, any function, let's call it F. Now, this message M is sent to this function F to be transformed using K1 to produce the first encrypted message, let's call it C1. Now C1 is used again to be encrypted via the same function F, but this time we will use the second key, key 2, to transform C1 into C2. The same process goes on until we reach CR-1 that goes to the same function F that uses KR to transform CR-1 into C into the final encrypted message that will be sent. In block cipher, we take any message M and we split it into multiple blocks. Let's call it M1, M2, and so on until we reach some block MR, such that all of these blocks should have the same size. Let me explain. If we, for example, have a message M that is 1024 bits, we can split this into 4 blocks, starting from the 0 bit until we reach 256 bit, and we call it M1. Then from 256 to 512 bit, and we call it M2. The third block should start from 512 till we reach 768, and we call it M3. And the final block from 768 until we reach 1024. We call it M4. All of these blocks have a size of 256 bits. After splitting the message M into 4 equally sized blocks, then we can use some encryption algorithm to encrypt each block. Call it E, using some key K to encrypt M1 and turn it into C, a cipher block. We use the same thing for all the blocks. In block cipher, we have modes of operations. Modes of operation allow us to encrypt large data whilst also having interesting security properties because each encryption algorithm works only on a fixed block. For example, let's take a look at electronic codebook, which is the simplest mode of operation. It is fast because it allows parallel encryption of blocks. However, it has no security. Because if some block M is identical to another block M2, for example, it will always produce the same cipher C. This will allow the attacker to infer more information on the key that is used to produce C. The second mode of operation, and that is the most used mode, called cipher block chaining, or CBC in short. We start first by randomly generating a number called the initialization vector. This initialization vector is used so that if we need to resend the message M a second time, it will produce in a different cipher. EV and K are the shared secrets between the sender and the recipient. We first start by taking the first block, M1. Then we use the XOR operation between M1 and EV, and the resulting output will be sent to be encrypted via the encryption algorithm using the key K to produce C. Then the result of the encryption algorithm, which is C1, will be also XORed with the second block, M2, and so on and so forth. In the recipient side, all we have to do is use the reverse operation of this circuit, C1, C2, C3, and so on. Let's assume that we received all the ciphered block. We just use exactly the reverse of each step. We notice that C1 was the result of the encryption algorithm. So what do? We use the decryption algorithm, DK. So this will give us something. It won't give us M1 because we noticed that M1 was not sent directly to K. It was XORed first with IV and then it was sent. So what we do is we use the same operation, XOR. We XOR it with IV to get M1. And then C2. We use the same with C2 except there's a difference. Instead of using IV to XOR it with the result of DK, we use C1. Because we notice right here that C1 was XORed with M2, then it was sent to the encryption algorithm. And the same thing for C3. Now, the problem is, what if, for example, I didn't receive C2 and I want to decrypt C3? So in order to decrypt C3, I use the same steps, and then when I reach the step when I need to XOR it with the previous ciphered block, C2, but remember, I don't have C2. So until the sender resends C2 and redo the encryption technique to get C2 and resend it, I am stuck in trying to decrypt C3 and the subsequent blocks. OFP, output feedback. It is the same as CBC, except decrypting blocks this time does not depend on previous ciphered block, which means if a certain block gets lost during the transmission, the decryption process by the recipient continues for the rest of the blocks. And that is because this time IV is being encrypted to produce R1. But this time, it is this result that gets forwarded to the second round of encryption. Instead of sending C1, we send R1. C2 right now does not depend on C1 to be decrypted. It depends on getting R2, which is the result of encrypting IV the first time to get R1, and then another time, and then a second time. So in other words, to decrypt any message MN, we need to encrypt IV n number of times using EK, and then finally we XOR it with that result. A stream cipher is a symmetric key cipher where plain text digits are combined with a pseudo-random cipher digit stream, also called key stream. In a stream cipher, each plain text digit is encrypted one at a time. So the main difference between stream cipher and block cipher is that block cipher we used fixed size equal blocks for encryption and decryption, but in stream cipher we use each digit is being encrypted and decrypted individually, just like when we previously talked about Caesar cipher. Caesar cipher is an example of a stream cipher where each letter in the plain text gets encrypted by its corresponding cipher to produce a cipher text. Now let's start and try to apply what we have learned so far about symmetric cryptography using one of the most used open source cryptographic libraries, and it is called OpenSSL. It has both symmetric and asymmetric cryptographic function. It can generate keys, encrypt and decrypt, generate digital signatures and hash functions, and many more. To get the installation, use this link from Windows. In Linux, it is already probably included in your distribution, especially if you're using Linux Mint, it is automatically installed. So you simply open a command line and type OpenSSL. And you will get something like this. So let's list some of the available commands that we have in OpenSSL. We type in list, then dash, commands. These are all the available commands that we can use. We can do something like this, OpenSSL, and then we press space, and then we type in the command that we want to execute, list dash commands. This will result in the same output. Let's first start by creating a directory that will hold our tests. We use mcd here for make directory. We'll call it symmetric test. We need to change the current directory to the newly created one by typing cd and the name of the newly created directory. Now we need a file that we use for encryption. Let's call it plain.txt using the touch command. Now plain.txt doesn't hold anything, obviously. It is empty. So we need to put some content in it using echo, and we will say hello world. Then we need to use the result of the echo command and put it inside this file, plain.txt. Now let's check the content of plain.txt again. It contains hello world. Now, as I said before, you can use OpenSSL in two different ways. You can type in OpenSSL, then pressing enter, and then you type in the full command here, or you can type in OpenSSL, then space, and you will type the same command. Both work equally the same. So in order to encrypt plain.txt, we say enc, which stands for encrypt. Then we need to specify the encryption algorithm that we are going to use. We are going to use AES, which is the most used encryption algorithm, with a key length of 256 bits. Then type in dash, then we need to specify the mode of operation. We'll say CBC. Then we'll type in dash N. Then we need to specify the path for the file that we want to encrypt. In this case, it is plain.txt, and it exists in the currently working directory. So we just need to type in the name, then type in dash out. Then you need to specify the name for the output. We will call it encrypted.bin for binary. Then we need to specify the subkey derivation algorithm by typing in dash PB, which stands for password base key derivation function 2. Now it prompts us to specify the password. We will use any password. Now it prompts us to verify the password that we entered. And the operation was successful. Now let's see if the file was created. Let's type in ls. Look, now we have a new file, encrypted.bin. Let's check the content of encrypted.bin. Type in cat encrypted.bin. As you can see, the content of encrypted.bin is completely unreadable. Now the decryption process is very similar. We type in OpenSSL, then we type in the name of the algorithm that we used for encryption, which is AES 256-CBC for CBC mode. Then we type in -d, which stands for decryption. Then we specify the file that we want to decrypt, -n as an input, encrypted.bin. Then we specify the outputs, -out. We will call it plain new.txt. Then we need to also specify the subkey derivation algorithm that was used, PBKDF2. It will prompt us for the password. We need to specify the same password, otherwise, of course, the operation would fail. And now the operation was successful. Let's type in ls. Now we have a newly created file, which is plain new.txt. Let's check the contents of this file. Type in ls, then plain new. Now look, it contains hello world. Let's compare it with the old plain.txt. It is the same.